Cool. Okay, it is somehow, some way, week 9. I'm Brian. We're going to be talking about mapping and maps today. Do we have any questions before we get started? Great. Then let's go. So today we're going to be covering 2 kinds of mapping. One that I'll call basic mapping, which is going to take advantage of ggplot2 in order to produce these maps. And the second one I'm going to call advanced mapping, which is going to take advantage of simple features that the GIS and like cartography nerds really enjoy. And that'll about do it. So the first thing I would like to do is plug this book. If you're interested in mapping, GIS, and geospatial analysis in R, do acquire this book. rspatial.org is a great resource as well. You may also consider taking Jono's class, Statistical Methods for Spatial Data. I myself have not taken the course, but I have worked through much of the syllabus. It's great. It often covers things more about sort of spatial statistics rather than like actually producing maps and stuff. But if you're producing maps, you're probably worried about the spatial statistics things going on. Also, there's a lot of great workshops that show up every so often through CSDE using things like ArcGIS and QGIS and all of that. And QGIS, like R, has like a wildly large user base because of its free 99. So let's get into basic mapping. Oh, I have something in the chat. ENVH, I'm not sure what ENVH is. Environmental health, maybe? 565, Intro to GIS for Public Health, is really good for mapping too. It occurs during the fall. You get to learn ArcGIS. Really cool. I think I had one of the younger members in my department also plug this class. She seemed to get a lot out of it. Yeah, I think I might have that syllabus as well. I'm very much a, hey, did you take that course? Send me the syllabus, please, kind of person. Cool. So ggplot2 and ggmap. So we're going to take that same data we were looking at a few weeks back that looked at the types of incidents at the SPD reported for a single day. This was a day in 2016, if I'm not mistaken. And we'll look at what all of those were. So same old, we're gonna use read CSV on wherever that is located. And we glimpse at this data frame and we get this. And I had noted before that this might be important later, that there's a longitude and latitude column. These are like the full-on, really, what's the word I'm looking for? Detailed longitude and latitude so that you can make really precise points. And we're going to be taking advantage of that information in order to produce these really quick plots. So we can use just longitude and latitude as coordinates in our ggplot without having to take very seriously any of the other information, like that it occurs on a sort of graphical space or that the globe is round kinds of things. We could just plot them as X and Y values in our regular aesthetics calls. So this is an ideal thing to do when you don't need to place the points over some map for reference. For instance, we are probably very familiar with the map of Seattle and can tell exactly what's going on when we look at these points. I can't think of times where I'm welcome in. I can't think of a lot of times where I would need to sort of skip having the map for a reference, but from time to time it'll happen. Also, note, I've added this chord fix layer here that'll evenly space our X and Y's. So it doesn't know that longitude and latitude are evenly spaced, but it will space them for you on a grid. But let's talk about ggmap because we almost always want to know that there's a map involved. So ggmap is a package that works with ggplot2 to plot spatial data directly on map images that are downloaded from Google Maps, OpenStreetMap, which is like Google Maps but free, and Stamen Maps, which has a lot of like, I don't want to call them like overly artistic, but they are a lot of like watercolory kinds of maps that you might be interested in. But what this package does for you. So first, it queries servers for a map using the getMap function at the location and the scale that you want. Then it plots the raster or the bitmap image as a ggplot object. Third, it lets you add more ggplot layers like points and density plots and text annotations on top of that initial map layer. And fourth, it has additional functions for interacting with Google Maps. For instance, getting distances by bike, which I believe is still the homework 7 ask. One thing to note is that Google Maps does require an API key, so you will have to get that. It's pretty easy. I haven't had to renew in a long time, but it used to be the case that you would have to like put a like credit card on file, because if you asked it too many things, like something in like the millions, they wanted your money. I don't know if that's still the case. So for the installation of ggmap, you can install it just like any other package, saying install.packages ggmap. But because the map APIs, i.e. Google, it uses changes frequently, sometimes you may need to get a newer development version of ggmap straight from the author's GitHub. This can be done using the remotes package. So if you just run these 2 lines, it will get the most recently updated version of ggmap right from the author's GitHub before it goes on the CRAN. And this is also the way that you would get other packages that are not on the CRAN whatsoever. Trying to think of like a good one. I'm not sure if the stand code for running like Bayesian analysis is still on the CRAN. I know that statistical rethinking like got off of there and all the Richard McElreath like follower people. Anyways, note that this may require compilation on your computer. On the front of the course website, there is a thing that describes how to make compilation available to your R instance for Mac and PC users. I don't know how Linux works, so don't ask me. Next, you can make quick maps using the qmplot function, so quick map plot function. It will automatically set the map region based on your data. So it knows where your longitudes and latitudes are, and then we'll be like, we'll put it right here on this map here. So here, all I've provided was the numeric latitude and longitude, and it placed the data points correctly on a raster map of Seattle. So it is exactly how it sounds. It is very quick to make little maps like this, and it is very pleasing to stakeholders who don't know how computers work, that you can make maps so quickly. Note that it only kind of works the way that ggplot works. So you can say like x equals longitude, but it's not an aesthetic call. It's just kind of free floating as an argument here in the quick map plot function. And also, if you want to set a particular thing, for instance, color to this particular purple, you would have to wrap it in this I function, which is used here to specify a constant rather than map values. But I think this is like pretty pleasing. I recognize all of these things. Okay, so both quick map plot and qmap are wrappers for a function called getMap that retrieves a base map layer. And you can provide a lot of options to that function in order to get what you'd like. So for instance, there's the location argument, this search query or numeric vector of longitude and latitude. So you could say like location UW, and it would find it for you as best as whatever the top option is. You can also say zoom equals, where lower numbers are farther away and higher numbers are closer to the ground. You can specify the source, things like Google, which we like Google Maps. I was a kid when Google Earth came out, and it was really cool. OSM for OpenStreetMaps. This is very general purpose, and you can make a lot of queries to it because it's not commodified like Google is. And also the Stamen maps, which are very aesthetically pleasing alternatives, but sometimes at the expense of what you're doing. Some map types you might want to look into. So Google types, they have a lot of ones you might be familiar with, like just the terrain or a satellite image of what you're looking at, the road map version of it. The Stamen types have things like watercolor and toner background that are pretty cool. And also you can specify whether or not you're gonna like print this out. So you could say color or black white. If you want to like sink a bunch of time during week 9, you can really mess around with location equals and see if you can get, you know, whatever the first Waffle House location or something. So you can add density layers to your quick map plots. So first we're going to call the QMPlot function with no geoms and then add density layers. So the way that we can do this is like ggplot, we're going to just use a plus sign to add additional layers. And so here what's going on, we have provided the SPD raw data to our quick map plot. We said geom equals blank, so we're not going to specify that we want dots at each of our longitudes and latitudes, but we are going to say that our longitude is X and our latitude is Y. And then our map type is going to be toner light. So that's what this background is. And then we're going to darken it a little bit in order to really make our density plot pop. And then we're going to use the stat density 2D, which I believe comes from the ggplot2 layers. And then we can specify things like the aesthetics. So we can say aesthetics fill equals the level. Note here that stat level indicates that we want fill to be based on level values calculated by the layer. And then we're going to say geom equals polygon. So we want the shape of our density to be a thing with a bunch of corners, I suppose. Our alpha is going to be set to 0.2 with no color. And then we're going to add a gradient fill scale in order to justify what, or in order to map how this is going to get filled in terms of like orange, yellow, red. But pretty neat, right? And crime's like, I don't know, where all of the biscuit places are. No, that's why I'm like, this looks like just a map of the biscuit places. Like this is Morsel, and here is Biscuit and Bean. And then there's like 3 or 4 right here downtown. And then the one in Northgate that I'm thinking of is like a different breakfast spot, but it does have good biscuits. So I don't know. That's like a project. You could you could write that one up. That's free for you to use. So let's label some points in our data. We could label particularly violent crimes. So let's say that we label assaults and robberies specifically in downtown. So first we can filter to downtown based on values eyeballed from our earlier map. Okay, so I just looked at the ones that were on this and I said, okay, downtown seems like it's between here and here. in order to get these values. So it's very non-scientific here what we're doing. And we just filtered based on those numeric values for our latitudes and longitudes. And then we made a data frame of just assaults and robberies based on this downtown filtered data. So we just said in this group of incidents, keep only the assaults and robberies. And then we're going to make a new column called assault label. That's going to be the description of whatever happened at that time. Okay, so now let's plot the events and label them with geom label. You can also use geom text. I'm using geom label here because it gives you that nice bright background. Geom text will just put the text on there with no background, so it'd be hard to look at.
It's like a braille.
Yes.
It's like a braille, like a geom.
Geom, what now?
The sound.
Oh, I see.
It's geom.
Geom, Brion.
Mhm.
Yeah. Okay, so we're going to specify for our quick map plot that our color is going to be fire brick now. I feel like I used fire brick so many times in this class. It is a nice red, but like there's other colors in the sea. And then we add this geom label layer with our data is going to be the assaults data that we had filtered to and created. Whereas up here, we used the downtown data, which didn't filter to just the assaults and robberies. And then our aesthetic here is going to be the labels equal to our assault label, which is going to be the description of the event. One thing that I don't like looking at this plot is that all of the labels are kind of overlapping here. I tend to not like this kind of thing. So one option that is available to us is the ggRepel package. So ggRepel just scoots things around so that you can read them. It's its own package that's just building out more stuff for ggplot. There's kind of a lot of packages that do this that just say like, okay, I'm not going to try to invent a whole nother thing. I just want to add this functionality to ggplot and make sure that it runs all the same stuff. And ggRepel is a really popular add-on that's not technically a ggplot2 thing, but they are, you know, friends. So here I've done the same thing, but I've used geom label repel, which is in the ggRepel package, and it will push them around so that nothing is overlapping and then draw lines to the particular points that they're interested in. So I highly recommend ggRepel not only for mapping, it's good for if you have like a scatter plot and you have some sort of like outliers that you want to be like, this is this particular case, ggRepel is great for that. Okay, so that was it for basic mapping. Do we have any questions? Okay, so let's get started with advanced mapping. So GIS and R things using the SF package. So some terminology I'm going to be saying kind of a lot in the next, half an hour are simple features, coordinate reference system, and shapefile. All of these things are going to be integral to us doing quote unquote advanced mapping. Excuse me. So the SF package, until recently, the main way to work with geospatial data in R was through the SP package. SP works well, and like you could still use it, and there are still some people who are really trying to make SP happen. But it does not store data the same way that most GIS packages do, and it can be kind of bulky and complicated. So part of the reason that SP people are not really trying to move is because like it's been bulky and complicated their whole lives, and they're just going to stick to it. The more recent SF package implements GIS standards of simple features in R. And part of that is that the SF people are partly the people who created SP, and some parts tidyverse people like the legend Jenny Bryan. So SF is integrated into the tidyverse. Shout out to Jenny Bryan again. And so you can just add geom SF into a ggplot2 after you've loaded the SF package, and it'll be sort of the canvas with which we will paint our maps for the rest of today. This package is somewhat new in that, like, I don't know, it's maybe a year and a half or 2 years old in terms of like really foundationally done and every bug is worked out kinds of things. And it's expected to replace SP eventually if those like SP nerds will change. The principal authors, I've said this, are sort of the same people from SP and some of the tidyverse people. But since SF is going to be sort of the new standard, we'll focus on it. So the first of those like vocabulary words is simple features. A simple feature is a single observation with some defined geospatial locations. Features are stored in special data frames called or class SF, and they have two properties. The first property is geometry. This properties describe a location, usually on Earth. Sometimes it's not on Earth. I used to work with an astronomer who talked about trying to build the geometry of mapping the moon, and I was like, okay, you're really talking past me now. Like I liked, I don't know, Nova enough, but so the geometry usually has 2 dimensions, but there's support for up to 4. I cannot, I don't know what you do with that 4th one, but I'm sure it's cool. Time, temporal shifts. Yeah, the only time I would think that you would need to draw a 4th dimension anything in social science is when you have you're doing a causal project and you need the whole like space of possible answers inside of a simplex. Is the only time I've ever drawn anything in 4 dimensions, and I feel like, why would that be on a map? I don't know. So maybe. Okay, so this is stored in a single reserved list column. So the column itself is a list of class SFC and contained a defined coordinate reference system. So sometimes you'll be working with simple feature data and you'll be like, this only has 100 rows. Why is it taking so long for me to open it or like change a column or something? It's because one of those columns is a whole list that's full of all of the possible shapes of how you're going to map the stuff. And those can get quite large. The second property are the attributes of the simple feature. Characteristics of the location, such as like population or something, can be stored here. These are non-spatial measures that describe the feature, right? So how many people there are in a county, or how many, I don't know, frogs there are at the pond. These have standard data frame columns or more like what we are used to seeing. So I noted that there was list columns. So within the list column, there can be like sub elements within that cell. And that's part of why the size of simple features data frames can get quite large. Oh, right. And list columns require special functions to manipulate. This includes removing them. So if you have a simple features data frame and you're like, I just want to select these 3 columns, it will keep the geometry column And so that's part of why you're like, this is going so slow. Why can't I get rid of this? Because there's special functions to do that we'll go over in a second. The next, for lack of a better word, vocabulary word, is coordinate reference systems. CRS will specify what location on Earth geometry coordinates are relative to. A way you can think about this is saying like, what location is 0, 0 when you're plotting something? What's the like Greenwich mean time of these dots? The most commonly used is WGS 84. It's the standard for Google Earth and the Department of Defense and many GPS satellites. There are two common ways to define a coordinate reference system in the SF package. The first is EPSG codes. These are numeric codes which refer to a predefined CRS. An example would be the WGS 84 sort of standard is written as 4326. There's also proj.4 strings. These are text strings of parameters that define a CRS. Some things like NAD 83, and they will look like this to help define what's the 0, 0 for what you're going to be plotting. And that's really important that you have commensurate CRS. For instance, because some of them are built to have just a slight curvature and some have quite a lot, and some are trying to get plot on a flat surface and trying to account for the dilation of Greenland and what have you. And the last word is shapefiles. This is geospatial data that is typically stored in shapefiles, or geospatial data is typically stored in shapefiles, which store geometric data as vectors with associated attributes. Okay, so shapefiles actually consist of multiple individual files. They're usually at least 3, but sometimes like more than 10. There's the .shp. This will be the feature geometry. So actually defining like the edge of the coast for the Olympics, for instance. The shape positional index, which I think helps make things contiguous, but I can't recall. And then .dbf is actually just like a wildly old version of how files were saved that can describe, are the attributes that describe the features. Often there will be a .prj file as well, defining the coordinate system. Other times you may have to define that coordinate system yourself. So now that we have those like 3 words, let's get into using the SF package. So a few of the select special features functions. So SF is huge and very feature rich. Here's a sample of some of the useful functions. Basically the ones that I've only ever used. I don't tend to make a lot of maps, but there's so much great resources that will help you. So the first is stread and stwrite, which will help you read and write shapefiles. And you might be saying to yourself, like, when would I be writing my own shapefile? I'll show you an example in a little bit. But one thing that you could do is like, you have a map and you realize that there's like, it didn't remove lakes and it filled them with information as if they were real. Not to say that lakes are fake. And you could get rid of those lakes on your map and then write the shape files back so that you could use them later without having to remove the water every time. geom_sf is the layer that you can add to ggplot objects. st as sf converts a data frame into an SF object. So sometimes your data frame will have like your geometry columns and the other stuff that you need, but you need to convert it to an SF object in order to take advantage of all these great SF functions. stjoin will join data by a spatial relationship. I think I've only ever done this once, and it was to join together 2 things that were, I had all the shape files for, but I needed to get them all both on the same map, is why I did that. ST transform will convert between coordinate reference systems. So like you started out on the standard WGS 84 and you need to switch over to a different one to help with this project. ST transform will get you there. ST drop geometry is the way that you get rid of the geometry column in your data frame. So remember this one, because I will always get upset and forget this one. So I'm hoping that you don't have that same feeling I get. ST relate will compute relationships between geometries like neighbor matrices so that you can tell whether or not things are touching and hanging out among your polygons. And there's also ST interpolate AW being aerial weighting. For some reason, somebody I know who works in maps more than I do says use the aerial package for this instead. So aerial weighting, if you don't know, is if you have like, let's say you have information that's at the tract level, but you have other information at the county level and you're supposed to report at the county level, you can aggregate those things up from the tract shapes into the larger umbrella of the county by assuming that all of the information in the tract is evenly distributed in the tract, and then you just sum it and aggregate it up to the larger shape. So the aerial package will get this done better for you than the SF package as of now. Okay, so I'm going to load some data in order to show off some of these features. I'm going to be working with the voting data from homework 5. You can obtain a shapefile of King County voting precincts from the county GIS data portal. It's really nice living in a big city and like they just have that line around. So we can load the file using the stread function. So here I've assigned to the precinct shape object the reading of our shape file for the voting precincts in King County. And there's some information that it will tell us when you run stread. It'll say things like, this is a simple feature with however many features. It's a multi-polygon that's on a X and Y flat surface. This is about as big as the box can get when you make your drawings, and its CRS is this one and not the one that we would consider standard, but that's okay. You can just convert them anyway. Okay, so I process some of the voting data. We don't need to get into all of the things that happened here, but suffice to say, I have joined the precinct data to what was basically the homework from 5 that I did in 20 lines, and then converted it to an SF object. Okay, so if we take a glimpse at this, we can see that per precinct in Seattle, we have percent Dem, how many people voted for Clinton and Kane, how many people of the voters voted for Trump and Pence, and what was the turnout like, as well as this column here that tells us the shape of the precinct that is specified like this. We'll note that this is a kind of unusual class that we're probably not used to seeing compared to like character or double. It'll have a geometry that consists of very many polygons in order to draw the shape of a precinct. And now we can make this voting map. So we can plot the SF geometry using the geom SF layer for our ggplot. So here I've supplied to ggplot our precinct votes simple features data frame. And the aesthetic is the percentage of people who voted for Dems in the presidential election in 2016. And then we added a geom SF layer, and then theme void, and I'm surprised that the legend position is not listening. Sorry, I'm not quite sure how that happened. It's over here, not down here. I'll think about that later. So our fill call to the aesthetics maps the colors inside of the precincts to our PDEM column. Maybe because offset of bottom to another line. I don't know. I think it might be because a lot of the things that I had to do to make these plots for the slides required that I use like an API key or something, but I also wanted the code to be available to all the students without my API key in it. So I would save the map to someplace else and then port it back in next to the code that makes it. And I think that I didn't add this part back when I made the, I don't know, I'm overly verbose right now. Okay, in the geom SF layer, we've also said size equals NA, and this will get rid of the precinct outlines because they are quite small. And if you have too many outlines, it'll be really tough to tell what all's going on. And then theme void just gets rid of all of the axes and backgrounds because that information is not useful to us here. Okay. Let's talk about the tidy census package. Tidy census can be used to search the ACS and decennial census for variables, then download them and automatically format them as tidy data frames. These data frames include geographical boundaries such as tracks. So it's really useful. I would say that I'm kind of lukewarm on tidy census. I know a lot of people who just like love it, and I don't know. I'm kind of an iPhones guy myself. This package utilizes the census API, so you'll need to obtain a census API key. And I wonder if this link still goes to the right place. Make sure that y'all can see it. Okay, this is the actual website that will take you to get a census API key. I know it looks like a scam. Okay, so you don't have to email me. This is what the legitimate website. This is the census.gov API key sign up. You just type in here, University of Washington and your UW address and say, yeah, and then submit the key request. And like 30 seconds later, you'll have this really long key that will allow you to just pull down the census at will. But it's real. It's okay. You don't have to email me. Okay, so now that we established that that website's real, the other thing is that we're using an API. This is an application program interface. It's a type of computer interface that exists as the native method of communication between computers, often via HTTP, and is usable through the HTTR package, sometimes called header. R packages that interface with websites and databases typically use APIs. APIs make accessing data easy while allowing websites to control the access, so they can sort of like levy how much information is being shared from their database to your computer through an API. There's a really good GitHub page that will describe this. But APIs can often be like really interesting places to get data. So like if you are like me and you work on workforce things and labor things, there's like a Indeed.com API that you can use to help get information, that kind of stuff. And there tends to be wrappers for them, like Tidy Census, depending on how big and useful the data is. Because a lot of places like Indeed or Monster don't actually want you to know all that information. Okay, so a few key Tidy Census functions. So first is the Census API key function. This will install a Census API key. So you'll need to run this prior to using any Tidy Census functions. And what you'll do is you can just put in the function the whole key that you'll get sent to your email in quotes. And you can also use the install equals true argument, perhaps, that will make sure that your version of R, that as is right now, will not need to run Census API key again ahead of doing any tidy census things. Yeah. The next one is load variables. This will load searchable variable lists. And you can say the year, so set the census year or the end year of the 5-year ACS, which they just released the 2020 5-year ACS, which I was worried they were not going to at all because there was low turnout for the 2020 survey, as you might imagine. You can also pick your data set. So you have access to things that are not just the ACS, or you can pick particular things under the ACS, like the March one, I believe, is the one that has things like who's an independent worker and who's a contingent worker, that kind of information. You can also use the get decennial function to load census variables in geographical boundaries. I don't know if they have the 1950 one now. They just released the 1950 like detailed census for researcher use, like, goodness, a month ago, 2 months ago. So I don't know if it's available through Tidy Census yet, in part because I don't think it's fully available to all researchers quite yet. And there you can pass arguments like variables, which is a vector of variable IDs. You can look up the decennial census variable IDs, the geography. So if you want information at the tract or block level, and what year census. And then if you pass geometry equals true, it'll give you your simple features geometry with it as well. You can do the same thing with a get ACS function call. So it can often be like pretty tough to search for variables because of just the way that how much information it is. So you can load the Tidy Census library and say, assign to this object the load variables, the year 2015, and you want the ACS 5-year estimates of the year 2015. And if you look through the 10th through 18th row, it'll say things like this, like this is a variable name and this is a variable name and so on. And the thing that it has inside is an estimate of how many people are male and 20 years old at like the block level, and so on for all of these different categories. But it can often be very difficult and I don't know what the word is, boring to read through all of these because there's so many and they're so specific like this. Very much a control F situation and very much a read the code book first situation. So you can get the data like this. Let's say we assign to the King County object the get ACS function. Our geography is going to be the tract level. The state is Washington. The county is King County, and our geometry is true in order to get our simple features geometry. And then the variables are going to be these two variables that I looked up, and the output is going to be wide. Note that output wide gives estimates at the end for like a point estimate as well as an error margin based on what it is, so that you can build confidence intervals around your estimates. So here it'll give us like this geo ID, which is just telling us like what tract, the name of the tract, an estimate of and margin of error for this variable and so on, and the geometry. Then we're going to process this. We can drop the margins of error and then rename the estimates, since we're not going to be using the margins of error, but I would like to know how to get those. And then we're going to make this any black measure. So this is anybody who self-identifies as black in King County. Yeah, and then we convert it to a proportion. And then in order to map this information, we're going to pipe the King County data into a ggplot. And the fill is going to be anybody who self-identifies as black as a proportion of that tract. The geom SF is going to be size equals NA, so we still don't have those lines around each of the tracts. And then we're going to add this chord SF layer. It has these arguments. So the first is the CRS. This will modify the coordinate reference system. We're going to make it the WGS84. I always have to look up how this is supposed to look, but since tidy census is so popular, it's really easy to find. And then datum equals NA removes graticule lines, which are geographical lines such as meridians and parallels, because we're only looking at King County, really. I don't think we need all of that. And so here is actually most of Washington. And then at the tract level tells you the percentage of people who identify as Black in any way. So pretty neat. But this is one thing that I did mention before, is that I'm like, this map is pretty cool, but kind of weird because it doesn't get rid of water. So I wrote this to function in order to remove the water. There are other ways to do this, but this is the way I could come up with using the SF package. There's another one that's called, it might be called R map reshaper, that has a function that will do this by itself, and probably faster than mine, but that's okay. So with a simple function and boundaries of water bodies in King County, we can replace that water with empty space. And so the way that I've decided to do this is create this st erase function and then use all of this. It's going to take an x and y argument. The x is going to go here, and st difference will subtract the geometry of one thing from another. And then let's look inside here. St combine merges all the geometries into one. So it takes all the things that are in our like y column and then makes them all just one big block geometry. The st union function resolves internal boundaries. So it's like, okay, we combined this big shape and then we've like dealt with all of these adjacent boundaries on the inside. St make valid will fix errors in the geometry between those like boundary lines because of things like water or mountains or slight miscalculations of the data, that kind of thing. And then I have this object called KC water. And then we look in the Tigris package, which is a really great way for you to just like get information about maps that maybe would be difficult to find otherwise. So Tigris has things like you can just get all of the water of all these maps, or like circle all of these urban areas, stuff like that. So here I've gotten the area water of the Washington King County maps. And then I would like that as a simple feature. And then I assign to the KC no water data frame, the King County data frame, and then erase the KC water data frame. And so this will make KC no water data frame. And when we plot it, now it looks a lot more like Western Washington. And I can be like, yeah, this is like, you know, where we are right now. Okay, so let's try this again. We're going to use my whole home state of Georgia. So we're going to assign to the PB state object the get ACS function at the tract level for the state of Georgia. Geometry equals true, so we can get our simple features. Those same variables and outputs wide. And we're going to do the same sort of calculations to get this percent any black figure. And then in order to make this plot, we will do the same thing. And so now you can like sort of port this code into making these really great plots. But how would we want to like maybe answer a question about this data. One thing we might want to do is add more layers on top of this information to make sense of this map. Like this map on its own is probably fine. And being from there makes, I don't know, this distribution very obvious to me. So this isn't telling me any information. But as with other ggplot2 layers, we can add additional geom-sf layers using new data. So this is really useful for adding points. So things like adding cities within states, adding crimes to police beats, adding lines. So things like street grids over tracks, train routes, that kind of thing. Adding outlines and highlights. So elevation contours, or perhaps urban boundaries. So we can add urban outlines. You can use the Tigris package to download urban boundaries and add them to our prior map. So we'll assign to the urbans object, the Tigris package, urban areas function, and class equals SF. And this is just going to give us all of the urban areas, more or less. And if we look at a glimpse of this, it'll tell us, things like Dixon, Illinois. But we're going to assign to the urban Georgia object this urbans data and filter to string detect name 10. So name 10 is here, which is just a city and a state, capital GA. So now what we can do is take our data and then start making this plot and then add another geom-sf layer using the urban Georgia information we got from the Tigris package and draw some outline and then add this inherit.aes equals false so that it does not have the same aesthetics as were given up here. Okay. And now I'm not sure how well that comes up on the screen back there, but it draws an outline for all of the urban areas. So things like Atlanta or Chattanooga up here. If you ever want to catch a Lookouts game, it's very fun. I really like going up to Chattanooga. Or Macon, Georgia. Macon used to boast that it had the most churches per capita in the world, and there's no way to measure that. It's really funny that there's, okay, so part of it is that in Macon, there are a ton of churches, but a lot of them are not registered as churches. So it's very difficult to even know if that's true. Or over here is Augusta. This is where they play the Masters in golf. One thing to note is that this is like a very black town and golf is a very white sport. And so there's a lot of like vacation among the people who live in Augusta when the Masters comes. And it's really fun. The not Masters things to do in Georgia while the Masters happen, excellent time. Highly recommend. And down here's Savannah, which is like one of those like small towns that's always just like, we have a really big St. Patrick's Day. Okay. So that was it for mapping. The homework 7 template is to practice making maps using the restaurant inspection data that we looked at last week. If you wish to submit it for bonus points, turn it in. I'll give you bonus points. I'm realizing it says turn it in via Canvas by 11:59 on next Tuesday. That's supposed to say next Wednesday. Homeworks are due on Wednesdays, so that's supposed to be next Wednesday. But yeah, do we have any questions? Okay. Next week, we're going to be talking about some data things, making nice tables, making regression tables, and virtually everything that I thought you might want to know about, but I did not think would fit into the class. So next week is kind of a hodgepodge, a potent potables, if you will. Well, thanks, y'all.